Alright, welcome back ladies and gentlemen to another lecture in this series on structural dynamics. Today we're talking about the responses of multi-degree of freedom systems using the state space formulation. So far what we've done is the discussion of responses of MDOF systems using the method of superposition, and really the limiting factor with that method is that you would need to know by heart the explicit solutions to the very specific forcing function. In the state space formulation, this is a one-size-fits-all type solution. By deriving or by converting our equation of motion to the state space formulation, we can use all sorts of simulation tools to give us our solutions, and this type of solution will be able to give you your steady state response and your complementary response, and it's very straightforward. I would say this is a magical tool that everyone needs to be aware of and needs to take advantage of course everyone in engineering. So what I want to do is to write down my multi-degree of freedom damped equation of motion, and I would have so here I have a dynamical system that is damped, and I have some sort of externally applied force PT that is getting applied onto my dynamical system. In a case like this, all my u dot, and u dot dot vectors are in fact n/1 vectors. So I can have u is equal to u1, u2, and I can have up to n many degrees of freedom. So pretty much u is an n/1 vector. At the same time, m, c, and k are n/n matrices. And in the same light, the force, or the externally applied force, is typically an n/1 vector of forces. So what I want to do now is to take this equation of motion and to convert it to state space formulation. We had an earlier session where we talked about the state space formulation, and we mentioned that we're converting the second order differential equation, which is our equation of motion, to a first order differential equation, and that makes things a little easier when we're doing things like simulations. And so let's see, we're doing state space, format. So that's what we're doing. So what we're going to start with is a change of variables. I'm going to call my u, and I'm going to refer to it by z1. So if I'm thinking about z1 derivative, I'm also thinking about u derivative. And then I introduce a second variable, and I call that z2. And this time z2 is actually equal to z1 derivative. So using these change of variables, what I can say is that z1 derivative is equal to z2. This is my first equation that I'm interested in. And then z2 derivative is equal to minus mass matrix inverse k z1 minus the same thing c z2 plus m inverse forcing function. And what I've essentially done is to look at my equation of motion and leave the acceleration term, this u dot dot term, on the left hand side and move everything else over to the right. and I end up with these two equations. This is the first one, and this is the second equation that I'm interested in. Alright, now what I'm going to do is to convert these two equations into matrix formulations. So this is what I'm going to have. Z1 and Z2. And this vector is equal to zero, I. 0 is a matrix of zeros, and it's n by n in dimensions. I is a vector of diagonal or identity matrix, and it's also n by n in dimension. And then in the second row I have minus m1 inverse, and then this is k minus m inverse c, and those are also n by n matrices. So let's just say n by n, n by n. And so this matrix as a whole is going to be 2n, excuse me, 2n by 2n. And so I have my original states, which are z1 and z2, and I have the derivatives of those states. And lastly, I have my forces, which are applied as follows. PT. Okay, so this first equation is really fundamental to the state space formulation, because now we've constructed our state matrix, which is really a variable which contains all the useful information from our structural system. It has all the masses, the stiffness terms, the damping terms. So really this is the brain of the simulation when we get to the simulation phase. And here we have the input matrix, and it really describes how forces are transformed when they enter the dynamical system. So now if I'm interested in pulling any of my variables out, for instance, I can say output, we always go with y when it comes to the output, can equal to u. I mean, let's say I'm interested in my u, or it could be u's could be displacements. I'm interested in the velocities and the accelerations. So I want all these very useful informations. Then I would have the converted variables, so z1, z2, and z2 derivative. And this thing is going to equal to I, 0, 0, I, minus m inverse k, minus m inverse c. I have my states z1 and z2, and I have my forcing elements. So this is what we have, PT. Notice that my states z1 and z2 and the force PT will always maintain the same format between these two equations. So I have my states equation and I have my output equation, and you can notice that my vectors z1 and z2 and PT are always maintain the same configuration, whereas I can change all these other elements to output the very specific thing that I'm interested in. So pretty much, in short, I can say my state space formulation gives me vector zt derivative, and this thing equals the matrix A multiplied by the state matrix ZT plus the input matrix B multiplied by the forces, the input forces PT, and I can have my outputs. Outputs can be customized. You can pretty much output whatever you want. B plus, there we go. And that's what we have. And again, here A is our state matrix. It contains all the dynamical properties of our dynamical system. B is our input matrix. C is our output matrix. And D is a throughput matrix. So D is how the externally applied force directly impacts our output. Okay? So once we have these matrices formulated, then what I can do is go on Matlab, and I can use the function SS, which stands for Statespace, and I can say I have a system, and this system is equal to SS, A, B, C, and D. Oops. There we go. Alright, let's do an example now. And with this example, we're going to be using Matlab and doing some real simulations. So in this example, I have a 3-degree of freedom system, and this system is a building. Okay, so this is a 2-story building with masses M and M on the first and the second floor, and on the third floor we have an antenna, and its mass is M over 1000. The reason why I am discussing this particular example is because in the recent years we've had a number of earthquakes which have resulted in damaged antennas in very tall buildings. And that has to do, these kinds of damages have to do with the mass ratio of the stories in these buildings and the mass of the antenna and how these masses interact. In fact, if you go on Google Images and look for damaged antennas due to earthquakes, you can get this very famous picture of the Tokyo Tower antenna. And this picture is from May of 2011, and this kind of damage was caused by the Tohoku earthquake, which was a really devastating earthquake that happened in Japan. So with this example, we're going to see really why these antennas get damaged and what the dynamics behind this whole scheme is. So I'm given this 3-story building, and what I want to do is to say that damping is proportional. I'm getting a 5% damping in all my modes. So I have zeta n, and n is 1, 2, and 3. I have a 3-degree of freedom system. I'm going to have 3 modes, and each of these modes will have a 5% damping, and that really means that I have proportional damping. Because as of now, we haven't really discussed any other kind of damping besides proportional damping in this course. So we're doing proportional. The stiffness matrix is already given to us, and I'm going to state it as follows. Okay, and that's our stiffness matrix. It's going to be symmetric, and it will have the units of kips per inches. The mass matrix is also similarly identified. It is 0.486, 1, 1, and 1/1000. And these are really parameters that I'm prescribing. I don't expect you to find these stiffness and mass matrices. The goal of this demonstration and example is to do state space formulation. We're not focused on the mass and stiffness matrices quite yet. So the units for this last term is kip second squared per inch. So that's what we have. And we are subjecting our two-story building plus the antenna to an earthquake ground motion acceleration. And this is going to be the, we're going to use the El Centro earthquake. That's quite a famous earthquake that happened in the 1940s, I believe. And we're going to use El Centro, and we're going to identify how each of these elements are going to be deformed, and also what their accelerations are going to be. So the first thing I want to do is to identify my damping matrix. My damping matrix is not given to me. The only thing that's given to me is my damping ratio, and I need to identify my damping matrix. Before doing that, I need to convert all my stiffness and mass matrices to the modal stiffness and mass matrices. And I'll explain why in a second. Okay, so the first thing I want to do is to say, to go on Matlab, plug in my stiffness and mass terms, and to get my mode shapes and my eigenvalues, which turn out to be my natural frequencies. And I get the following: Eig, K, M. So I can use this Eig function that Matlab offers, and I can plug in my stiffness and mass matrices, and these are what I would get. And lambda, which is my eigenvalues, will be equal to my natural frequencies squared. Alright, so now I'm going to open Matlab and pretty much explain what I've done here. I have my Matlab script here where I am inputting my mass and stiffness matrices as I have prescribed them in the example. And then what I'm doing is to identify my phi's, which are my mode shapes, and my lambdas, which are my eigenvalues, using this Eig function. And then I'm using the sort and the square root commands to identify my natural frequencies. And why I need to sort them is because Matlab does not give you your natural frequencies in order. Ideally, they should be ordered from the smallest first to the largest, because the smallest tends to be your first natural frequency and so forth. So I need to sort them. So once we do this, I'm going to run these first couple commands. I get natural frequencies that are equal to 6.12 radians per second, 6.45, and 41.8. Okay, now the second thing I want to do is to identify my modal matrices. So if I want my modal mass matrix, now that I know my phi, or excuse me, my phi, I can say phi transposed mass phi is equal to my modal mass. I could say the same thing about my stiffness matrix. So K modal is equal to phi transposed K phi, and that'll give me my stiffness matrix. These two matrices will be diagonal. Modal matrices are always diagonal. And then what I can do is to identify my modal damping matrix. So I can say modal damping is equal to a diagonal matrix where the off-diagonal terms are zeros, and the diagonal terms are as follows. I have 2mm1 zeta omega n 1. I have 2mm2, so that's the second of the diagonal terms, zeta omega n 2. And lastly, I have 2mm3. That's the final diagonal element in the mass modal matrix. And then I have zeta omega n 3. And then once I have my modal damping matrix, I can easily find my damping matrix, which is phi transposed inverse, modal damping matrix, and phi inverse. So let's go on Matlab and see how we did that. Here it goes. Here I am getting my modal damping, mass and stiffness matrices, and the phi is identified as follows. And I have my proportional damping ratio, and here I'm identifying the diagonal terms. And lastly, I am converting back to get my damping matrix. So I have my modal damping, and here I have my actual damping matrix. So I'm going to compile all of this. Let's compile that, and alright, everything looks good. So let's move on. Now the next thing I want to do is to identify my equation of motion. This is an example that includes earthquakes, so my forces are going to look a little different. So step 3, we're doing equation of motion. With the equation of motion, the inertial term or the mass term is always dependent on the absolute accelerations. So I have u dot dot here, which is the acceleration of the floors, plus I have the acceleration of the base. And this is really the earthquake acceleration. Now, the damping and the stiffness terms are dependent on the relative motion. And so we only have the u's. The u's are our relative motion, so the motion of each of the floors with reference to the ground motion. And this whole thing is equal to 0. And then what I can say is to write mu. I'm going to move this ground acceleration to the right hand side of my equation, and I'll have okay, this is what I'm going to have. Something we like to do is to put this I term here, and this I is a vector of 1s, and the reason for that is that my ground acceleration is not actually a vector. So when I'm multiplying a non-vector or a constant by a matrix, I'll get a matrix as the output, but I want a vector here instead of a matrix. So I put these vector of 1s, which convert my input into a vector of ground accelerations, and that allows each of my floors to be equally multiplied by the ground acceleration. Okay, so what I'm going to do now is to move everything to the right hand side of my equation except for my acceleration term. So what I'll have is u dot dot is equal to then I, and that's what we're going to have. And I get a number of matrices, A being my state matrix. So I'll have I minus M inverse K, M inverse C. My B matrix will be 0, I. My C matrix will be I, 0. And I'll explain in a second what I'm doing with the C matrix. I mentioned at the beginning of this example that I was interested in the deformations and the accelerations of each of these floors. So with the first row, I am dragging the deformations out, and with the second row, I'm getting all my accelerations out. And you know, if you're thinking about the state space formulation, my C matrix gets multiplied by Z1 and Z2. And here Z1 is displacements, so Z2s are cancelled out and I'm getting my displacements, and in the second row I'm getting my accelerations. Alright, so let's erase that. And lastly, my D matrix will be a vector of zeros. The reason for that is the following. If I write my equation of motion and I say I am interested in my absolute acceleration for each floor as the output, then what happens is, so I'm interested in the absolute acceleration. So what happens is I can say I want to add m xg to both sides of my equation. So these two will give us the absolute acceleration, and on the right hand side of this equation we're going to get a force that is equal to 0. So by putting a d value that is equal to 0 here instead of I am pulling the absolute acceleration instead of the relative acceleration. If I had I here instead of the 0, I would have the relative accelerations as the output. So that's really what that means, and so that's really it. I open Matlab again, and I plug in my A, B, and C matrices. I put a S in front of my state space matrices just to avoid confusions with other variables. And lastly, I use this SS command to plug in all these matrices, and BDG stands for my building. I have a 2-3 story building. So we're going to run this. It's going to be okay. Yeah, it all sounds good. And the next thing I want to do is to compile my ground motion acceleration and to really show you what it looks like. And here it is. This is my El Centro acceleration. The units are in inches per seconds squared. And it's going to last roughly 50 seconds. So that's something we're going to be dealing with. And then I use the lsim command on Matlab. I plug in my system, which is the building. I plug in the input acceleration. Here is where you would, the second term is where you would put your externally applied force, and the third element is your vector of times. So your time vector, your force vector, and your system. And then I plot all my figures. So let's do that. Okay, here we go. So here what I'm saying is that my story 1, story 2, and antenna are getting deformed as follows. Story 1 has the formation of roughly plus minus 2 inches. That is almost 5 centimeters if you're thinking in the metric system. Story 2 is plus minus 5 inches. So I would say that's around 12-13 centimeters if you're thinking about the metric system. And the antenna is moving a lot. It's moving by 50 inches. And this really has to go down to the this goes down to the dynamics of having a very small mass over a number of big masses. Once they accelerate, they result in the small mass accelerating much more and getting deformed much more, and incurring a lot of damages. And in the second column here, I'm looking at my accelerations, and these accelerations have been normalized to units of g. So g is the ground acceleration. So I have plus minus half a g, plus minus half a g in story 1 and 2. And with the antenna, I get almost 5 g's. Now, I don't know about you, but no material is going to last this much acceleration unless it's a fighter jet of some sort. Structural systems, especially buildings, are not going to last these kinds of accelerations. So this is how the Tohoku earthquake pretty much damaged the antenna on the Tokyo Tower. And you can look that up. That took place in 2011. I would say the last thing we want to discuss with this session is the concept of frequency response functions. If I show you the very bottom part of my code, what I'm doing here is using the Bodhi command to identify the frequency response of my antenna. And I want to compile this again. And here I'll be showing you what the antenna, or how the antenna will be behaving in the frequency domain for both displacement and acceleration. So what I want you to focus on is this graph on the top, and how the horizontal axis is all the different frequencies. So I have a 0 up to 1,000 for the frequencies in hertz. And on the vertical axis, I have the amplitude, which is really the amplification of any kind of input force. So here our input force is ground motion acceleration, and I'm showing you how this acceleration is going to amplify with the different frequencies. And what we're seeing is that from the I would say 0.5 to 3 hertz amplitude is where we're getting amplification in the antenna. And this is bad news, because for a ground motion like the El Centro motion, the bandwidth of the motion is pretty much the 0.5 to 4.5 hertz bandwidth. And most earthquakes tend to be in the same region as well. And anytime we have this kind of these kinds of tendencies in the antenna, we're going to see damage. So if you're the engineer, you might want to change that. You might want to move this frequency maybe down the aisle a little, maybe to 10 hertz, to avoid the massive amplifications that we're seeing. All right, in the future sessions, I'll talk more about frequency response and why it's so important, and why it makes things so easy to see and to analyze. In the meanwhile, I hope you found this session to be useful, and I will see